Hello, everyone. Whilst you're practicing, it's easy to reach for a calculator when working with powers. However, many questions involving indices appear in the non-calculator paper. That's why it's important to understand the laws of indices and know how to simplify these expressions without relying on a calculator. In this video, we'll begin with a quick overview of the laws of indices before applying them to a range of exam-style questions. By the end of this lesson, you'll be able to simplify expressions involving powers, apply the laws of indices confidently, solve exam-style questions without using a calculator. Let's have a look at the types of questions we'll be covering. We'll work through questions involving a single variable, multiple variables, fractions, and positive, negative, and fractional powers. We'll also see how prime factor decomposition can sometimes make these questions much easier to simplify. As the examples progress, we'll combine different laws of indices, just as you might need to do in an exam. Let's start by looking at the laws of indices we'll be using throughout the video. I'd recommend writing them down before we move on, as we'll refer to them in every example. Remember, in maths, understanding a rule is only the first step. Real progress comes from applying it, so I'd encourage you to pause the video and try each example yourself before checking the solution. The first rule tells us what happens when we multiply powers with the same base. When the bases are the same, we keep the base exactly as it is and add the exponents. Let's look at the example. Here, both powers have the same base, which is 4. So we keep the 4 exactly as it is and simply add the exponents. 3 plus 2 gives us 5, so our final answer is 4 to the power of 5. The second rule applies when we divide powers with the same base. Just like the previous rule, the base stays exactly the same. The difference is that this time, instead of adding the exponents, we subtract them. Let's look at the example. We have 4 cubed divided by 4 squared. The base is 4 in both powers, so we keep the 4 exactly as it is. Then we subtract the exponents. 3 minus 2 is 1, so we get 4 to the power of 1. Any number to the power of 1 is equal to itself, so 4 to the power of 1 is simply 4. As before, this rule only works when the bases are identical. The third rule tells us what happens when one power is raised to another power. In this case, we keep the base and multiply the exponents. Let's look at the example. We have 4 cubed, all squared. The base stays exactly the same. Then we multiply the exponents. 3 times 2 is 6, so the expression becomes 4 to the power of 6. The fourth rule applies when the exponent is negative. A negative exponent tells us to take the reciprocal and make the exponent positive. We have 4 to the power of negative 3. We can think of 4 as 4 over 1. Taking the reciprocal means swapping the numerator and the denominator. So 4 over 1 becomes 1 over 4, and the exponent becomes positive 3. Remember that the exponent applies to both the numerator and the denominator. Since 1 raised to any real power is always 1, we simply write 1 in the numerator. So 4 to the power of negative 3 is equal to 1 over 4 cubed. The same idea applies when the base is already a fraction. Here we have 4/5, all raised to the power of negative 3. We take the reciprocal by swapping the numerator and the denominator. So 4/5 becomes 5/4, and the exponent becomes positive 3. We then apply the exponent to both the numerator and the denominator, giving us 5 cubed over 4 cubed. The fifth rule applies when the exponent is a fraction. The numerator of the fraction works as a normal exponent. The denominator becomes the index of the root. Let's see how this works in the example. We have 4 to the power of 2/3. The numerator is 2, so we square the 4. The denominator is 3, so we take the cube root. This means that 4 to the power of 2/3 is equal to the cube root of 4 squared. Before we move on to the examples, let's quickly look at a few useful facts. Any number raised to the power of 1 is simply the number itself. Any non-zero number raised to the power of 0 is equal to 1. Now, let's put these rules into practice. Let's start with the first example. We have a to the power of 5 multiplied by a to the power of 4. Notice that we're multiplying two powers with the same base. That tells us we need to use the product rule. We keep the base, which is a, exactly the same, and add the exponents. 5 plus 4 is 9, so the expression simplifies to a to the power of 9. Let's move on to the second example. We have 4x cubed multiplied by 3x to the power of 5. A useful strategy here is to group the coefficients together and the powers of x together. This gives us 4 multiplied by 3 and x cubed multiplied by x to the power of 5. For the coefficients, we simply multiply them together. 4 multiplied by 3 is 12. For the powers of x, we use the product rule. The base stays the same, so we keep x and add the exponents. 3 plus 5 is 8. So the expression simplifies to 12x to the power of 8. Before we move on to the next example, if you're enjoying the video so far, please give it a like and consider subscribing to the channel. Let's move on to the third example. We have y to the power of 7 divided by y cubed. Notice that we're dividing two powers with the same base. That tells us we need to use the quotient rule. We keep the base, which is y, exactly the same and subtract the exponents. 7 minus 3 is 4, so the expression simplifies to y to the power of 4. Now let's look at example 4. Simplify 2x to the power of 4y squared multiplied by 6x cubed y. We're multiplying powers with the same base, so we'll use the product rule. Before we continue, notice that the y in the second term doesn't have an exponent. Whenever a variable doesn't have an exponent written, its exponent is 1. Just like in the previous example, let's group the coefficients together, the x terms together, and the y terms together. This gives us 2 multiplied by 6, x to the power of 4 multiplied by x cubed, and y squared multiplied by y to the power of 1. For the coefficients, we simply multiply them together, giving us 12. For the powers of x, we apply the product rule. We keep the base and add the exponents, giving us x to the power of 4 plus 3. We do exactly the same for the powers of y. We keep the base and add the exponents, giving us a y to the power of 2 plus 1. Simplifying the exponents, the expression becomes 12, x to the power of 7, y cubed. Now let's look at example 5. Simplify. 5 to the power of 3 divided by 5 to the power of negative 2. We're dividing two powers with the same base, so we'll use the quotient rule. We keep the base exactly the same and subtract the exponents. This gives us 5 to the power of 3 minus negative 2. 3 minus negative 2 becomes 3 plus 2. So the expression becomes 5 to the power of 3 plus 2. Finally, 3 plus 2 is 5. So the expression simplifies to 5 to the power of 5. Now let's look at example 6. Simplify 81 to the power of negative 3/4. Here we'll need to use two of the laws we've just learned: the rule for negative powers and the rule for fractional powers. Let's start with the negative exponent. We can think of 81 as 81 over 1. Applying the negative power rule means taking the reciprocal and making the exponent positive. This gives us 1 over 81 to the power of 3/4. Remember that 1 raised to any real power is always 1, so we simply write 1 in the numerator. Now let's apply the fractional power rule. The denominator tells us which root to take, while the numerator tells us the power. So this becomes 1 over the 4th root of 81 cubed. To simplify this further, we'll write 81 as a product of its prime factors. This is a step I'd always recommend whenever the coefficient isn't a prime number, and especially when you're working with roots. Although your final answer should be written as a number, expressing it as powers of its prime factors often makes the intermediate steps much easier to simplify. If you're not sure how to do prime factor decomposition, I've linked a video in the description that explains it step by step. 81 is equal to 3 to the power of 4. Substituting this into the expression gives us 1 over the 4th root of 3 to the power of 4, all raised to the power of 3. We now apply the power of a power rule, so we keep the base and multiply the exponents. 4 multiplied by 3 is 12, giving us 1 over the 4th root of 3 to the power of 12. We can then write the 4th root as a power of 1/4. This gives us 1 over 3 to the power of 12 divided by 4. 12 divided by 4 is 3, so we get 1 over 3 cubed. Finally, 3 cubed is 27, so the expression simplifies to 1 over 27. Now let's look at example 7. Simplify. 4x to the power of 6 divided by 9x squared, all raised to the power of 3/2. Here we'll use a combination of the laws of indices shown on the right. Let's begin by simplifying the expression inside the brackets. We'll leave 4 over 9 as a fraction and apply the quotient rule to the powers of x. The base stays the same, and we subtract the exponents. This gives us 4/9 x to the power of 6 minus 2, all raised to the power of 3/2. 6 minus 2 is 4, so we get 4/9 x to the power of 4, all raised to the power of 3/2. We will use the power of a power rule here to simplify the expression. Remember, with the power of a power rule, we keep the base and multiply the exponents. The exponent of 3/2 applies to everything inside the brackets. So we can split the expression into 4/9 to the power of 3/2 multiplied by x to the power of 12 over 2. Now let's simplify 4/9 to the power of 3/2 using the fractional power rule. The denominator tells us to take the square root, while the numerator tells us to cube the result. This gives us the square root of 4 cubed divided by the square root of 9 cubed multiplied by x to the power of 6. The square root of 4 cubed is 2 cubed, and the square root of 9 cubed is 3 cubed. So the expression becomes 2 cubed divided by 3 cubed multiplied by x to the power of 6. Finally, 2 cubed is 8, and 3 cubed is 27. So the expression simplifies to 8 over 27x to the power of 6. Now let's look at example 8. Find the value of n. 5 to the power of n is equal to the 7th root of 5. Pause the video here and see if you can solve it on your own. Then press play to check the solution. Let's go through it together. We'll use the fractional power rule. Remember, the denominator of the fraction becomes the index of the root, while the numerator becomes the exponent of the number inside the root. There is no exponent written on the 5, so its exponent is 1. This means that the 7th root of 5 can be written as 5 to the power of 1/7. The bases are the same, so the exponents must be equal. Therefore, n is equal to 1/7. Now let's look at example 9. Simplify. 729u to the power of 24, all raised to the power of 2/3. The exponent of 2/3 applies to both 729 and u to the power of 24. We apply the power of a power rule. We keep the base and multiply the exponents, so we get 729 to the power of 2/3, multiplied by u to the power of 48 over 3. To simplify 729 to the power of 2/3, we write 729 as a power of its prime factors. 729 is equal to 3 to the power of 6. This gives us 3 to the power of 6, all raised to the power of 2/3, multiplied by u to the power of 16. We apply the power of a power rule again. We keep the base and multiply the exponents. 6 multiplied by 2/3 gives us 12/3. So we get 3 to the power of 12/3, multiplied by u to the power of 16. 12 divided by 3 is 4, so this simplifies to 3 to the power of 4, multiplied by u to the power of 16. Finally, 3 to the power of 4 is 81. So the expression simplifies to 81u to the power of 16. Now, let's look at the final example. Simplify. 4096 x to the power of 4096, all raised to the power of 1/4. Pause the video here and see if you can solve it on your own. Then press play to check the solution. Let's compare our answers. If you applied the power of a power rule followed by the fractional power rule, you should have obtained 64x to the power of 1024. And that's all for this video. Thank you very much for watching, and I'll see you in the next one.